Welcome to Catalyst Medhub, where we ignite understanding and make learning easier. In our today's class, still under carbohydrate chemistry, we shall be discussing on properties and reactions of carbohydrates. The properties and reactions of the carbohydrates, there is physical property of the carbohydrate and chemical properties or the reactions of carbohydrate. Now, physical properties of carbohydrate. Physical properties. The physical properties of carbohydrates include 1. Taste. 2. Optical activity. 3. Hygroscopic nature. 4. Appearance. 5. Solubility. 6. Melting point. So these are the common physical properties of carbohydrate. 1. Taste. Some of the carbohydrates, especially some monosaccharide and disaccharide, they are usually sweet. Optical activity. Carbohydrates, they exhibit optical activity, that is the ability to rotate a plane polarized light due to the presence of asymmetric carbon atom. Hygroscopic nature. Some carbohydrates also, they have ability to absorb moisture. Appearance. Majority of the carbohydrates, they are crystalline in nature. They are white and crystalline in nature. Solubility. Carbohydrates, majorly, they are soluble in water due to the presence of polyhydroxyl group. Melting point, they have high melting point. So this is about the physical properties of carbohydrates. Next is the chemical properties or reactions of carbohydrates. Chemical properties or reactions of carbohydrates. Under this, we will have 1. Reduction of carbohydrates. 2. Oxidation of carbohydrates. 3. Reducing properties. 4. Osazone formation. 5. Dehydration of carbohydrates. And lastly, tautomerism or enolization. So these are the chemical properties or reactions of carbohydrates. The first one is reduction of carbohydrates. First, reduction of carbohydrates. It simply means the reaction between carbohydrates with the reducing agent. If aldehyde or ketone functional group of the carbohydrate reacts with reducing agent such as sodium amalgam or nascent hydrogen, they will form alcohol. We have carbohydrates reacting with reducing agents, it will form alcohol. The general reaction is then in the presence of nascent hydrogen, we will be having alcohol. What we don't need is we just add hydrogen to the aldehyde or ketone functional group. Now, this is a general reaction pattern of reduction of carbohydrate using reducing agent. And each monosaccharide, they have the alcohol that they give after undergoing reduction. Example, glucose will give sorbitol. Mannose will give mannitol. Galactose will give decitol. Ribose will give ribitol. and fructose will give sorbitol and mannitol. So these are the monosaccharides with their corresponding alcohol that you will give if they undergo reduction. Glucose will give sorbitol, mannose will give mannitol, galactose will give decitol, ribose will give ribitol, and fructose will give sorbitol and mannitol. So that is on the reduction of carbohydrate. Next one is oxidation of carbohydrate. Oxidation of carbohydrate. Oxidation of carbohydrate simply means addition of oxygen to the carbohydrates. Many carbohydrates such as monosaccharide and disaccharide, they have ability to react with oxidizing agents. Depending on the oxidizing agent that is used, the terminal aldehyde functional group can be oxidized, the alcohol functional group can be oxidized, or both group can be oxidized. Now let's take glucose as an example. This is the structure of glucose: 1, 2, 3, 4, 5, 6. OH, H, and H. Now we say that in the oxidation, depending on the oxidizing agent used, the terminal carbonyl functional group can be oxidized, and the last carbon with OH can also be oxidized. Now this is glucose. If the terminal carbonyl functional group is oxidized, we will be having gluconic acid. 1, 2, 3, 4, 5, 6. Now we say that if the terminal aldehyde functional group is oxidized, we will be having gluconic acid. If the terminal aldehyde functional group is oxidized, we will be having gluconic acid. But if it is the terminal alcohol group that is oxidized, we will be having glucuronic acid. So this is the structure of glucuronic acid. 1, 2, 3, 4, 5, 6. So here now, it is the terminal alcohol functional group that will be oxidized. Here, so this is glucuronic acid. Now, if both the aldehyde and the alcohol functional group they are oxidized, we'll be having glucaric acid. So this is the structure of glucaric acid. 1, 2, 3, 4, 5, 6. Both the aldehyde functional group will be oxidized as well as the alcohol functional group will be oxidized. So the gluconic acid if the terminal aldehyde functional group is oxidized, and glucuronic acid if the terminal alcohol group is oxidized. Now, if both aldehyde and the terminal alcohol group is oxidized, we'll be having glucaric acid. Now, the oxidizing agent for the aldehyde or the terminal alcohol functional group is usually bromine water, while by the oxidizing agent to oxidize both aldehyde and alcohol functional group is usually concentrated HNO3. So that is on the oxidation of carbohydrate. Next one is reducing property. Carbohydrate usually serve as a reducing property, especially disaccharide. Disaccharide, due to their reducing property, they are further divided into the two, reducing sugars and non-reducing sugar. The reducing sugar, they are the sugar that can act as a reducing agent, and it's because they possess free aldehyde or ketone functional group. Example, we can be having maltose and lactose. While by the non-reducing sugar, they cannot act as a reducing agent because they do not have free aldehyde or free ketone in their structure. Example, sucrose and keralose. Now, the reducing property of the sugar can be tested using various tests such as Benedict test. Sugars or the reducing sugar, they reduces cupric ion of copper sulfate into cupreous hydroxide or cupreous oxide. Cupreous hydroxide is usually yellow in color, while the cupreous oxide is red in color. That is the general test for the sugar. Next one is Osazone Formation. Osazone Formation. The first thing to know about Osazone Formation is that the first and Osazone Formation is involve first and second carbon atoms in the structure of the molecule. Now, carbohydrates such as monosaccharide, they react with phenyl hydrazine to form osazone, which is a color compound. Now, we said carbohydrates such as monosaccharide containing aldehyde or ketone functional group, they react with phenyl hydrazine to form osazone. Carbohydrates such as monosaccharide that contain aldehyde or free ketone functional group, they react with phenyl hydrazine to form osazone. And osazone formation involve first and second carbon atoms. Now let's take glucose as an example to demonstrate osazone formation. Glucose is C double bond with hydrogen, OH and H. Here is our R. Because since we say that osazone formation involve only first and second carbon, we just demonstrate using first and second carbon. Now this glucose here will react with phenyl hydrazine. Phenyl hydrazine is which is H2N NH C6H5. This is phenyl hydrazine. The mechanism behind it is that the first carbon will react with it, then you will react your product again with another phenyl hydrazine so that the second carbon will react with phenyl hydrazine. So our first product will give us, instead of having double bond O, we will now attach hydrogen to it. NHC6H5, then COR and H. The first carbon has reacted with phenyl hydrazine. In this condition, we will be having glucohydrazone. So the first product here is glucohydrazone. Again, this glucohydrazone will further react again with another phenyl hydrazine to give us glucosazone. The glucohydrazone will react again with another phenyl hydrazine to give us glucosazone. So another reaction will take place. NH C6H5. Then the second carbon will now carry its own hydrazine, NH C6H and R. So this is glucosazone now. Glucosazone. Since you say that carbon number 1 and carbon number 2, they are involved in osazone formation. Carbon number 1 is destroyed during osazone formation. Then glucose, fructose and mannose, they have the same osazone formation, which is needle-shaped crystals. That is on osazone formation. Next one is dehydration of carbohydrates. Carbohydrates react with dehydrating agent such as concentrated H2SO4 to give sulfura or hydroxymethyl sulfura derivative. We say that carbohydrates reacting with a dehydrating agent such as concentrated H2SO4, they will give sulfura or hydroxymethyl sulfura. All pentoses they will give sulfura, while by hexoses they will give hydroxymethyl sulfura. Now, if pentoses such as ribose, they react with concentrated H2SO4, they will give sulfura. So this sulfura is given by pentoses. While by if hexoses they are being dehydrated with concentrated SO4, they will give hydrogen methyl sulfura. Example, glucose and hexose. So hydrogen methyl sulfura is given by hexoses. So, and the reaction goes like this. This is the structure of pentose. Pentose, example, ribose has 5 carbon. That is 1, 2, 3, 4, and 5. This is pentose. OH, 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 and CH2, OH. Ribose have OH oriented to one side throughout. So now ribose react with concentrated H2SO4. Concentrated H2SO4, which will now remove water. That is 3 molecules of water. We will remove 3 molecules of water. H2O, H2O, H2O. We will be left with 1 oxygen left. So from here, our structure, that is the fuller structure of pentose, will now be CHO is 5 carbon. 1, 2, 3, 4, 5. The first carbon, which is CHO, then sulfura will now be, you'll be having single bond, double bond, single bond, double bond. And here, this is the structure that will be left. And this structure is the sulfura of pentose. The example of carbon number 5 we use is ribose. So this is the sulfura. Now let's do for the glucose to give us hydrogen methyl sulfura. Glucose is carbon number 6, which will now be 1, 2, 3, 4, 5, 6. CH2OH. Here we'll be having hydrogen, OH, OH, and OH. Reacting with concentrated H2SO4, reacting with concentrated H2SO4, and remove 3 molecules of water. Our product will now be 1, 2, 3, 4, 5, and 6. Carbon number 6. CHO, here is CH2OH, then we'll be having single bond, double bond, single bond, double bond with single bond. From here, hydrogen, hydrogen. We can see from here, we are having this hydrogen methyl now. CH2OH is hydrogen methyl. And if you look at the structure of pentoses, there is no hydrogen methyl. It's just sulfura. But C carbon upward is sulfura. But CH2OH is hydrogen methyl. That is the reason why I'm saying hexoses such as glucose will give us hydrogen methyl sulfura. While by the pentoses such as ribose will just give us sulfura. The next and the last reaction of carbohydrate is tautomerism or enolization. Tautomerism or enolization. Tautomerism is just a phenomenon whereby an atom is being moved between an unstable compound to become stable. So in carbohydrates such as glucose, if it is left in an alkaline medium for several hours, it will convert to fructose and mannose through an intermediate called enediol. The formation of enediol is known as enolization. Tautomerism or enolization of carbohydrates is that in mid-alkaline medium, carbohydrates that contain free aldehyde or free ketones, they will tautomerize to form enediol. And enediol is just an intermediate, and it is a compound where a 2 hydroxyl group is attached to the double-bonded carbon atom. Now let's demonstrate tautomerization using glucose. We said in mid-alkaline medium, glucose will be converted to fructose and mannose through the formation of an intermediate called enediol. So this is the structure of glucose: CHO, COH, and R. This area is the remaining alkyl group. We say that the glucose, when left in an alkaline medium, will be converted to fructose and mannose with the formation of an intermediate called enediol. This is the structure of glucose now. Now, let's form enediol. We say that enediol is a structure where two hydroxyl group is attached to double bonded carbon. So here we'll be having this double bond, carbon, and R, we're having OH. This is the structure of any diol. So from here, we can form fructose and we can form mannose. For the fructose, we know that the fructose is ketosis. It contains its own functional group. So let's take up here as our fructose. So we have CH2OH, then the second carbon with double bond and R. This is now our fructose. Another one we will be having is mannose. So this will now be the structure of the mannose. CHOCH, then with R. So this is fructose and this mannose. We have come to the end of properties and reactions of carbohydrates. Kindly subscribe, like, comment, and share. Don't forget to turn on your notification bell so that you don't miss any new video.